So if you can hear me, let's start. Chemical reactions. So all we did last week was basically all SS1 work. So for the focus of this week, we'll be looking at some key areas in SS2, which is obviously some of the topics we will encounter. Chemist overview, we'll talk about periodic table during this section. And that is the first two topics in the scheme for SS2 periodic table. And after periodic table, we should have chemical reactions, which is the build up to that. So chemical reactions, we check the scheme is for week 3 and week 4. So we'll just quickly look at what we can cover as fast as we can under chemical reactions. If you can hear me, let me know, or is the voice too low?
No, I can hear you.
Okay. So can anybody help us with various types of chemical reactions that you know? Common chemical reactions. I mean, that should be the first thing to use to induce or like your set induction when you enter class as a student to list some chemical reactions, types of chemical reactions that you can do. Maybe let's start from there. Madam Busayo, can you help us? Types of chemical reactions. Or
I think reversible reaction.
okay, there's reversible reactions. Decomposition reaction.
Exothermic.
We have maybe we have reversible, like you said, reversible reactions. We have decomposition reaction, decomposition. We have displacement. Displacement reaction. Can anyone help us again with another one? A very common one, we have redox reaction. Which other one again?
Combination.
Combination reaction, thank you. And so on and so forth. But we get to these aspects. So if these are the types, at least with this, the students now know what we'll be looking at. So this is, let's start from the beginning. So chemical reaction, if you are writing, you can write. By definition, a chemical equation is a shorthand. So let them know. A chemical equation is a shorthand method of using chemical formula to present a chemical or physical change. Did you get that? The chemical equation is a shorthand method. It's a shorthand method of using chemical equation or chemical formula rather. Chemical formula to present a chemical or physical change. That is what the chemical equation is. It's a shorthand method of representing chemical formulas. That's okay.
Sorry, of representing chemical formula.
Or like come again, a chemical equation is a shorthand method. Is a shorthand method of using chemical formula to present a chemical or physical change. Is a shorthand method of using chemical formula to present a chemical or physical change. Did you get that now?
Yes, yes, sir.
Thank you. So in every chemical equation, there are always two sides. What are the two sides? We have, let's say I have this as a typical equation, just as an example. This side is called my left-hand side, while this is my right-hand side. So in every chemical equation, there are two sides, the left-hand side and the right-hand side. On the left-hand side, that is where you always have your reactant. And on the right-hand side is your product.
Okay.
So also let the student know that the substance which undergoes combination, or the substance which is combining or disappearing, are called reactants. That is this one now. Substance which is combining or disappearing are called reactants, while the substance, the new substance which is formed, is known as the product. Got it?
Yes, sir.
Okay. So let's quickly write the subheading there. Rate of,
Yes.
okay, thank you. Rate of chemical equation, rate of chemical reaction, the rate of a chemical reaction, the rate of a chemical reaction, rate of chemical reaction. Are we ready?
Yes.
So rate of chemical reaction is defined as the rate at which a new substance is formed, or the reactant is used up per unit time. The rate of the chemical reaction is defined as the rate at which a new substance is formed, or the reactants are used up, reactants, if you are putting S, reactants are used up per unit time. Is that okay? So if you are to express that mathematically, rate of chemical reaction is equals to, are we ready?
Yes, we're ready.
Okay, if you write it for the sake of space, that's why I will detail this part now. So the rate of the chemical reaction is equals to, up here is change in concentration of reactant or product. Change in concentration of reactant or product. That's what you write up. That is your, I think that should be numerator. Right. Change in concentration of reactant or product. Then down here is time. So change in concentration of reactant or product, all over time taken. That is the formula to calculate rate of a chemical reaction. Are we ready?
Yes.
Then, if you are to represent it symbolically, the rate of chemical reaction is equals to change in concentration over change in time. Where C stands for concentration, small t stands for time. Any question?
Oh.
Can I move on?
Yes.
Okay, thank you. I'm sure you are flowing. So the next thing we'll look at now is chemical reactions on the basis of rate of reaction. It's a subheading. Chemical reactions on the basis of rate of reaction. Chemical reaction on the basis of rate of chemical reaction. Chemical reactions on the basis of rate of reaction. So on the basis of rate of reaction, there are basically three types of chemical reactions. Okay. So on the basis of rate of reaction, there are three types of chemical reaction. One is moderately. Are we there? Moderately
Yes.
slow reaction. Moderately slow reaction, that is one. I'll just listen, I'll explain them. Next is slow reaction. And the last one is fast reaction. So these are the three basic types of chemical reaction. I remember when I started the class, we listed types of chemical reactions such as reversible, decomposition, and the rest. That is just types. But on the basis that is putting consideration on the rate of chemical reaction, we have basically three types of reaction. So the reaction could either be moderately slow, it could be slow, or it could be fast. So for the first one, moderately slow reaction, just as the name implies, all of them, the reaction is moderately slow when it is neither too fast or too slow for a new product to be formed. That means the reaction rate is intermediate between slow and fast. Any question? Then the next one is a slow reaction. Again, just as the name implies too, a reaction is said to be slow when it takes a longer time for the reaction to proceed to completion. Any question? That is what we call a slow reaction. When it takes a longer time for the reaction to get to completion or for a new product to be formed. That is a slow reaction. A very good example of a slow reaction is rusting of iron. Iron will not rust overnight. Iron will not rust in 2 days. It takes weeks, months, or if not even years for the iron to get rust. Also, another example of such reaction is decaying process. Decaying process. Those reactions are very slow reactions. Madam Esther, are you with us?
Yes, I am.
Okay, hope I'm not too fast as in terms of the rate of reaction now.
No.
Am I too slow?
No, you're not. Thank you.
So where will we now place our pace of movement?
It's number one, moderately slow reaction.
Okay, that's on the light time. Now let's come to the last one, fast reaction. These type of reactions get to completion very, very fast, or it takes lesser time for a new product to be formed. Example of such reaction is, you can demonstrate this one with your students by showing neutralization reaction. Remember when you react acid and base together, it gives you salt and water. But we always add the indicator to the base. Then as you begin to add the acid gradually, the color will change. The best type I always use for my students is I always use phenolphthalein indicator. That one is more catchy. Once you add phenolphthalein indicator to your base, what is the color? Can anybody try?
I think it's pink.
Okay, yes, pink. Then as you begin to add the acid, once you get a complete neutralization, what will be the color change?
Yellow.
No, the color change is colorless. It returned back to the way it was before you added the base. Sorry, before you added the indicator to the base, just like color of water. When you demonstrate that with students, they will just be wow. You just see the chat say, hey, because immediately just one drop of the acid come inside that solution, it will change the color once you get to a complete neutralization. That's a very good example of a fast reaction. Okay. But aside that, we also have another example of fast reaction, such as substitution reactions in alkanes. And we also have substitution reactions in organic compounds, such as alkanes, like in the case of methane reacting with chlorine in the presence of sunlight. That's an example of such type of reaction whereby the product that is formed is called tetrachloromethane. So that is that for the types of chemical reaction on the basis of chemical rate of chemical reaction. Any question?
No question.
Okay, let's do
Please,
some.
excuse me, please.
Yes.
I didn't get the example you gave on the moderately slow reaction. Do you have any example?
Okay, for moderately slow reaction, I can't lay my hands on any example now, but maybe at the end of the class, we'll just see if we can Google some examples, but I'm sure there's no really example I can lay my hands on now, so I didn't give example for that. So maybe we'll look into that. But at least give it on slow and fast.
Okay.
Okay. So can we move on now?
Yes, we can.
Okay. Under this area, there are few calculations, although very rare, you will see the calculations. But if you are prepared students for JAM, let them be exposed to these calculations. Hence, I will look at two calculations under rate of chemical reaction. Do we have anybody teaching SS2? Or that has taught SS2?
Yes.
Okay. Did you come across any calculation when you're teaching them this topic?
Yes, few.
Few, yes, very few calculations. Maybe in WAEC, I hardly see, but I used to see it in JAM questions. So it's important you let them know. Do some few calculations under this. So in respect to that, let's write this question down. What is the rate of, are you there?
Yes.
Okay. What is the rate of hydrolysis? What is the rate of hydrolysis of 42 grams, that is 42 G? What is the rate of hydrolysis of 42 grams of sodium ethanoate in 1 DNQ vessel? What is the rate of hydrolysis of 42 grams of sodium ethanoate in 1 DNQ vessel if the process takes 30 seconds? Are you with me?
Yes, sir.
Okay, did we get the question?
Yes, I did.
Okay, so formula for rate is equals to what? Rate of reaction. You can simply use the symbol, which is change in concentration over change in time. Any question?
No question for now.
Okay, let me show you something now, because questions varies. What do we mean by change? Change simply means that if you are given two concentrations, such as initial concentration and the final concentration, you will subtract to get change. If you are given two times, maybe the first time and the second time, you subtract to get change in time, then divide. Is that okay?
Okay.
But if, like in a situation like this, we're not given two different concentrations and we're not given two time, you just divide your concentration by time and you get your answer. Is that okay?
Yes, sir.
Okay. So the question now is, what is the formula for calculating concentration? Because in this question, we're not given concentration, but we're given parameters that we can use to calculate for concentration. So concentration in mole DNQ is equals to number of moles all over volume in DNQ. There is no issue with this formula. I don't think anybody has issue with this formula.
No.
Okay, but I'll ask a simple question. Let your student know concentration, volume must be in DNQ. Volume can either be in CNQ or DNQ. What's the relationship between those two? CNQ and DNQ. $1,000 CM cube is equal to 1 dm cube. So if the solution or the concentration, the volume is in CM cube, change it to dm cube before you use this formula. But if the volume is in dm cube, just put it here directly and you solve. Now, how do we change CM cube to dm cube? Simply divide by 1000. Divide your CM cube by 1000 to give you the expected answer in dm cube. So that is that. You let them know that simple calculations. Are we okay?
Yes.
Okay. Then again, what is the formula for number of moles? Number of moles is equals to given
Mass over molar.
given mass, or just say mass over molar mass. Why am I doing all this? Because in that question, I was given the mass, that is 42 grams of sodium ethanoate. I can calculate the molar mass, and I was also given volume, so I can get the concentration. And then I was given the time, so it's very straightforward calculation. Are we ready now?
Yes.
Can I clean the first line?
Yes, sir.
Okay. So what is the formula for sodium ethanoate? Because it was not given in the question. They didn't give us formula. They only wrote sodium ethanoate. Sodium ethanoate is CH3COONA. That is the formula for sodium ethanoate. So I'm going to do this now. Molar mass of CH3COONA equals to, what is the relative atomic mass for carbon? Carbon.
12.
Yeah, thank you. Carbon is always 12, so that would be 12 plus hydrogen is always 1, but we have 3 atoms here. 1 times 3 will give me 3 plus 12 again, which is this carbon. Then we have 2 oxygen. 1 oxygen is 16, so I say 16 times 2. Then sodium is 3. Is that okay? Any question? If you do this addition, you should get 82 grams. That is your molar mass. Are you with me?
I will give you people mercy. Yes, I'm with you.
Okay. So now we will now look at the number of moles now. Number of moles equals to, what is the given mass in the question?
42.
42. What is our molar mass now? 82.
82.
So we divide this, we should get 0.5. If you have a calculator, then you can use your phone. That will give me 0.5 moles. Then I will now say concentration now in mole dm cube will now be 0.5, which is my mole, over volume, which was 1. And that's still give me 0.5 mole dm cube. So that is my concentration. Any question? Any question?
No question.
Okay. So if you are done, let's quickly clean this part off. Remember, all this we are doing is not actual. We are not yet done. The question was to calculate rate of reaction. So we can now say recall rate of reaction equals to change in concentration by change in time. And our concentration now is 0.5, which I have gotten. What is the time in the question? Time.
Time is 30 seconds.
30 seconds. Okay. Divide 0.5 divided by 30. You have a calculator, can you help us? I've been the one doing the calculation since, so let me shift this one out to you. 0.5 divided by 30. You can use your phone.
0.016 or 0.017.
0.017.
Seven.
Okay? 0.017. Remember, units in WAEC, wrong unit, no score. Right unit, right score. Then I always tell my students to be on the safe side. If you don't know the unit, leave it like this.
Like that.
Yes. If it's like this, the examiner will mark it good. But if you put the wrong unit, they will mark it bad. That is this final answer now as it's marked. You will lose the mark for the final answer. But again, it's also very simple how to get unit. What is the unit for concentration?
Mole per DMQ.
Okay, so my final answer
Mole
now
per DMQ.
0.017 mole DMQ. This is divided. Time was in seconds per second, like this. So this is the unit for the answer. So this is the answer now. 0.017 mole per DMQ per second. Any question?
No.
Okay, thank you very much. Another example before we move on now. Example 2. 0.052 mole DMQ. 0.052 mole DMQ of a reactant B. 0.052 mole DMQ of a reactant B, capital letter B, was consumed in 12 seconds. What is the rate of the reaction? Any question?
Sorry, what
Please,
is the
please.
Okay, let me come again with the question. 0.052 mole DMQ. 0.052 mole DMQ of a reactant B. Of a reactant B was consumed in 12 seconds. What is the rate of the reaction? What is the rate of the reaction? Is that taken?
Yes, sir.
Okay, so you just simply write the formula again. Rate of reaction equals to change in concentration over change in time. So examiner marking is theory, correct substitution. Now, what is the concentration here? It was already given, so this one is just a one-way solution. Concentration was 0.052 all over the time, which is 12 seconds. So there's no need of calculating long calculation like we did in the first one. Divide this, someone help us out. What do we have? Anybody?
We have 0.004.
0.004. Okay. For what?
3.
Okay, I'll leave it at 3 decimal places there. 0.004 units mole DMQ per second. That's the answer. Any issue?
Oh, no issue.
Okay, so we'll move on quickly. We're supposed to have types of chemical reactions next, but there's no issue with that one now. Any problem with that? There's no need. So we can leave that one to move on to the next thing. Otherwise, that was supposed to be types of chemical reaction, and then we'll go to one very important aspect now. This first part will still be over in the next 6 minutes. So once what we do is once it go off, you come back immediately. Let's continue. Not like 10 minutes extra, no break. So we'll just continue. Are we ready?
Yeah.
Okay, so if you are ready, let's write collision theory. Collision theory. This aspect always comes out in WAEC. The students, most of the time, they always ask them, state collision theory, list factors that affect the rate of a chemical reaction. Maybe list 4 and explain 3 or like that. So let them know. If you are ready, let me move on. Are you ready?
Yes, we're ready.
Okay, so collision theory. This theory states that for every chemical reaction to occur, it states that for every chemical reaction to occur, there must be effective collision. Underline that word, effective. Theory states that for every chemical reaction to occur, there must be effective collision between the reacting particles. Are you with me?
Sorry, there must be effective
Collision. There must be effective
Okay.
collision between the reacting particles. Please emphasis on the word effective. So if, for example, a child says, if you remove that word effective and just say there must be collision between it, is not correct. So there must be effective collision between the reacting particles. Is that okay?
Yes, sir.
So, which means, now don't write, let me just explain something now. We said for every chemical reaction to occur, remember we always have two sides in a chemical reaction, the reactant and the what?
The product.
And the product. And for me to form a product, the particles of the reactant must collide to give me the product. That is what collision theory is talking about. And then I said, underline that word effective. Effective means that obviously there must be collision between the reacting particle, but it is not all the collision that results to the formation of a new product. That is why we say underline effective. So it is only a collision that is effective that results to the formation of a new product. Are you with me? Okay. Now, again, link it like this when teaching your students. Not everybody that is going to school now will make money at the same time. Okay? Or not everybody that is going to school now will graduate at the same time. That's why they say, like, 20 friends cannot play together for 20 years. Okay? So, that the particles are colliding, that we are all together in the same class learning, does not mean everybody will have first class. So that is what it's. Now, what then is effective collision? Who can help us? 5 minutes to come back. Okay. You have an idea?
I want to try.
Okay, try. Yes, there's no harm in trying.
Okay, effective collision based on what we explained is the collision that results in the formation of a product.
Okay, yes, thank you. But that definition is good, but something, the key ingredient there are missing. So it's more or less like, let me use this word, a layman's definition of effective collision. Sorry to use that word. So now, this is what we mean by effective collision. You can write, a collision is effective if the colliding particles has energy greater than the activation energy. A collision is effective if the colliding particles has energy greater than the activation energy of the reacting system.
Has energy greater than the
activation energy of the reacting system. They have energy greater than the activation energy of the reacting system. 3 minutes to go for this section. Is that taking? Hmm? Do we get it?
Yeah. Yes, sir.
Okay. Now again, I've dropped another word there again. Activation energy. So which means if the colliding particle don't have energy that is greater than the activation energy, the collision is not effective. So if the colliding particle have energy greater than the activation energy, then the collision is effective and a new product will be formed. That's okay.
Yes, sir.
Now again, what then now is now activation energy? Because they used to tell the students all these things. Define activation energy or state collision theory. So we stop here or we define activation energy and come back again? Hello?
Hi.
Okay. Okay. So at this point, I want to just let these 2 minutes go. Okay, let's just define activation energy. I'm sure we should be able to define in the next 2 minutes. So you can write activation energy is the minimum amount of energy needed for a chemical reaction to occur. Activation energy is the minimum amount of energy needed for a chemical reaction to occur. Is that okay? When we want to talk about types of chemical reaction in terms of exothermic and endothermic, I will show you something there. Hello?
Yes.
Okay. Can you see the board?
Yes.
Okay. So I have a diagram here. This is a diagram of an energy profile diagram. On this side is my reactant. On this side is my product. This is like a graph, 0. Let me say this is 10, 20, 30, 40, 50. Did you get this? A minute more. So, hello?
Hi.
Okay, so you can see here now, this is reactant. This is product.
Okay.
So for me to get to this product, the reacting particle must collide and climb this hill and come down like this.
Okay.
But if the reacting particle don't have energy enough to climb this hill, that is to break this barrier, they will fall back and still remain as reactants. So such type of collision are ineffective. That means they don't have enough energy to break this barrier. So, and how do we calculate activation energy? The symbol for activation energy is EA. So if you are writing, you can put this one somewhere. That's the symbol for activation energy, EA. So EA is calculated like this, from here to here. That is the distance between the reactant to the top here, which is called transition state or activated complex.